Hello, everybody. I'm a little unused to speaking to a quiet room, but I'll presume you're all.
Hi, Doug.
Hi, Doug.
Hi, Doug. We are all here.
Thank you.
Hi, Doug.
Okay. I insist my students get up and say good morning every morning at 8:30 in the morning. They don't always appreciate that, but here we are. All right, so this talk is resource management for dynamic function distribution with parcel and work queue. So my name is Douglas Thain. I hail from the University of Notre Dame in Indiana, and this is work joint with Ben Tovar, Tan Sun Fung, and Barry Sly Delgado, who are all members of my research group here. So the work I'm talking about today is the result of an ongoing collaboration with the parcel group. And so we have a lot of fun working together for I think it's 2 or 3 years now. It's always hard to tell what with COVID, how much time has elapsed. And I realized just as we were going to press here that both of these slides are slightly outdated in that we both have new logos. And so I appreciate the new ones showing up in earlier talks. But of course, I don't have to describe Parcel at Parcel Fest here. But if you haven't heard of WorkQ, WorkQ is a system developed here at Notre Dame that provides scalable, portable, and robust distributed execution across large-scale distributed systems. And it's a system that can be applied in many different contexts. So you can build custom applications with it, or you can plug it in underneath systems that provide higher level services. And so Parcel and WorkQ go very well together, and that Parcel solves all manner of problems related to how do you compose and organize and express a workflow. And then when we put the two together, WorkQ can handle some of the problems of how do we get the task in the right place at the right time, understand its resource consumption, figure out if it failed or not, and make sure that we harness all of our resources effectively. So this is just sort of a picture of how things fit together. So in this work here, we haven't done anything to change the high-level Parcel Python interface. We haven't done anything to change the Parcel data flow kernel. That puts everything in order. But most of the work described here happens in this middle layer, which is the driver that is the Parcel WorkQ executor. And so we've had a lot of interaction with Kyle and Ben and Yadu about how to provide this interface between the workflow system and the underlying executor. Briefly, the mechanics of how it works is that the WorkQ manager provides a submit wait interface. And so the job of the Parcel WorkQ executor is to take tasks as they become ready to run and transform them into a fully materialized task that consists of some input resources, some output resources, and then those are scheduled to available workers over on the right-hand side. And so we can have a very large number of workers, thousands or tens of thousands, and we have a variety of facilities for running those workers on existing resource managers. So you can take these workers and easily get them going on HT Condor, PBS, Slurm, what have you. And the reason for doing this sort of overlay scheduling is primarily because many of these systems are very good at managing compute, but they're not so good at managing data, or particularly in managing data in a way that's specific to a given application. So by creating an overlay system with its own workers and its own policies, then you can achieve your own scheduling and resource management requirements independently of the underlying system. Now, conventionally, WorkQ works at the Unix process level. And so usually when you define a WorkQ application, you think of it in terms of executables that I'm sending over with input files and output files. But part of the transformation here is, of course, that Parcel works with Python functions. And so what the Parcel WorkQ executor does here is ensure that we have the right Python environment in place and transform those function invocations into something that can live in a Unix process execution interface. And so one of the nice side effects of having an overlay network is that you can deploy it across all manner of resources. So if you want to get a very large application going, you can take workers and submit them to a wide variety of systems. And we think of this as sort of a personal cloud that calls home and makes all these resources available to a Python application that just perceives itself to be submitting tasks and getting results back. So if you want to set up a Parcel plus WorkQ application, there isn't a lot to do. So you have to specify the WorkQ executor and then indicate a port you want to listen on, a project name if you want this to be reported back and made available with real-time status information. And then there are a few other options to be set up there if you want security, and you can control caching and a variety of other things. But for the most part, you pop in the configuration and run your standard applications. Now, I don't want to talk too much about the executor, but I want to talk more about two problems that come up generally in distributed applications and that have some peculiarities that result from the fact that we are dealing with function invocations, which are often a smaller, more granular, more lightweight thing than running applications in a cluster. And so the two questions I want to think about today are, number one, what resources should be assigned to a given function invocation? And by resources, I mean number of CPUs, memory, GPUs, disk space, really anything that can run out on the executing machine. And connected to this is a question of what software dependencies does this function need? Because after all, if we're going to take a function and throw it over the fence and run it somewhere else, it can't execute unless it has all of the code assets that it needs to operate correctly. Now, both of these questions can be answered to some degree manually. So if you are an expert in all the underlying details of these systems, you can come along and tell us exactly what we need to know. Oh, this function uses 1.5 megabytes of memory and it needs all these particular imports. And if you know all those things, then great, you put them in and we're done. But for the most part, we find that users who are attempting to prosecute science are not particularly interested in fine-tuning these things. And in fact, the answers may be very complicated, and the answers may change on a daily basis as software evolves. So really what we want is a system that can discover the answers to these sort of questions automatically at runtime without requiring the user to. So let me give a quick example. So, I think the typical use case of Parcel is to pack a whole lot of function executions into a many-core node. So let's say for the sake of argument here, I have a bunch of workers that have 12 cores and 12 gigabytes of RAM. So over on the right-hand side there, you can see I have a worker. The worker is running a bunch of functions. And over on the left side is our Parcel stack, where we have a Python application that declares some functions it wants to run. It's sitting on top of the Parcel data flow kernel, which is sitting on top of the work queue manager process. So the application declares some functions it wants to run. It generates a whole bunch of function invocations that are noted over there on the left-hand side. And now we have to decide how many resources do we assign to each of those function invocations. Well, let's make a guess. I don't know. Maybe it's 2 gigabytes of memory per function invocation. So in this picture over here, I've shown that we can pack 6 function invocations into one worker at one time without wasting resources. Now, is it the right answer? I don't know. It's hard to tell. If you're a computer science type, you'd say, well, maybe I'll sit here all day long and I'll turn that number up and down and see what happens. Maybe if those functions are crashing, what I need to do is assign 4 gigabytes of memory to each function. If that's enough, then they'll start succeeding. And that's a fine thing to do. And you might be wondering, why are we arguing over a gigabyte here and a gigabyte there? Because after all, it's 2 gigabytes among friends. But as you can see from this picture, if I double the memory dedicated to a single function execution, okay, yes, I'm consuming more memory, but I've also halved my concurrency of it, because now I can only run 3 functions at a time on a given worker. So that means I'm also going to have my concurrency across the whole system unless I'm also willing to double the total number of resources that I'm willing to allocate. So this choice of how much memory do I allocate turns out to be really important in the big picture of the application. And it gets more complicated because maybe I have 2 different kinds of functions. It doesn't follow that they're going to have the same kind of profile. And we'd like to think that every instance of a function behaves the same, but they don't. So you might have a function A here that some invocations use a lot of memory, other invocations don't use so much. So what do we do to solve this problem? Well, first of all, we have to know how much memory things use, how much resources in general things use. And so here we're relying on some work done by Ben Tovar to create a lightweight function monitor. And this is something that we attach to every Python process in a Parcel work queue stack. And so every time we're about to run a function, a Parcel function, on the other side over at the worker, we insert this LFM, which is a little bit of Python code, also a little bit of C, into the Python interpreter. And every time we run that function, we are going to fork a process. Sounds a little dangerous, but what that does is it allows us to put a box around the resources consumed by that function and monitor what's going on using standard operating system measures. And then when that process is done, it goes away and reports its resource usage back to the parent. And so now if we're running lots of processes, then we're going to be, lots of functions, we're going to end up with lots of processes and containers. But in practice, this turns out to be reasonably efficient because we can rely on copy and write and similar measures in the operating system kernel. And so this was described in a recent paper at IPDPS with the Parcel group here. And we can hide this pretty nicely behind Python interfaces here. So you'll see here from resource monitor, import monitored. And then all I have to do is stick a decorator in front of a function. And then whenever I invoke that function, it will come back with the result that it computes, as well as the resources that it consumed. So this example here shows just running a function and getting back its memory consumption and wall time. There are about 100 other properties that you can monitor if you care to. All right, so now we can monitor functions. What are we going to do with this? Well, so one of my students, Thain here, has been working with Colmena. And I believe you heard something about Colmena yesterday from Logan Ward. And so a particular application we're looking at here is XTB. And so XTB exhibits the same pattern of Python application, data flow kernel, scheduler, and it has functions of various types. In this case, there are functions that perform molecular simulations, and then there are functions that perform inference on the result of those simulations. So we have two categories of functions. What resources do they consume, and how should we go about packing them into workers? Well, the first thing we did is go out and measure them. And there's some kind of peculiar results here. So if you look at the graph on the left here, what we have is function invocations over time. So each dot is a function invocation. And the y-axis shows the memory consumption of that function invocation. And I think it was a little surprising to us just how noisy this data was. We sort of expected that functions of the same type would have very similar behavior, but they don't. Now, why is that? Well, in simulation, it could be random seeds. Could depend on how deep your simulation gets into the details, depending on the conditions it explores. It could be variance in data sets if we're doing a data process in the application. There are a lot of reasons why this could be, but it leads us with a difficult question, which is how much memory should we allocate to each function? We could go out and allocate 30 gigabytes each function invocation. And if we did that, everything would succeed, but then we would not be maximizing our concurrency. On the other hand, we might go out and say, let's be stingy. I'm going to allocate 2 gigabytes to every function call, see if it works. And then if it doesn't work, then I'll try it again with a larger quantity of resources. And there, what we'd be doing is we'd be packing more functions in, but we would run the risk of some of them failing, and then we'd have to retry them. So what are we going to do about it? Well, the approach that Thain has come up with here is to try to figure out what the appropriate division between these attempts is at runtime. So the idea here is if we can find the right division, what we should do is try to run most functions with a moderate amount of memory and see if they work. And for those few that don't work, then we should run them with a larger amount. But the problem is to figure out the boundaries between those buckets. So I think I don't have time to explain exactly what that algorithm is. But if you're interested, you should come to the Works workshop at Supercomputing and read Thain's paper and learn all about it. But he has come up with an algorithm for doing this, and it works incrementally. So we go out and we execute tasks, and as we build up information about the behavior of different tasks, we learn what is the ideal division between buckets, keeping in mind that we want most of them to succeed if we can, but we have the option of retrying them if they fail. Now, the overall result of this depends a lot on the behavior of applications. So we've looked at a variety of applications with different distributions, and sometimes you get just a little bit of improvement, but sometimes you get a huge improvement if there's a huge range of variation in functions. So right now we're taking this technique, I should say Thain is taking this technique and working it into WorkQ and Parcel so that we'll be able to deploy this automatically with applications that show a wide variety of behavior. Second problem. Runtime dependency management. So I'm going to come back to my picture here. Here's our stack of an application with Parcel with WorkQ. And so we have functions over here that want to run on a worker over there. The question is, how do we get the right code in the right place? I mean, at the simplest level, all you have to do is take that function, pickle it, and then send the pickled function over and run it. But do you take just the text of that function? You take the function and the functions that it calls? How deep do you go? Do you follow all the way down into Parcel and TensorFlow and who knows what else may be in that application and bring it over? It turns out to be a really sticky problem to solve. And to generalize it a little bit, I'll just say that our manager over here runs in a particular software environment. And how that environment got there is sometimes a little fuzzy because the user may have come along and installed software from a variety of places. They've got conda packages, maybe they installed stuff by a pip. And it's also the case that for applications under development, you just have some local source there. I edited some Python today, and now I want to punch go and make it happen. And this makes things a little tricky because maybe on the other side, we could get our conda packages and we could get our pip packages, no problem. But we also have to bring over the things that are peculiar to this application on this node and do so in a consistent way. We want the tasks on the other side to be able to execute in a consistent environment, the same on every workers, a minimal environment. We don't want it to be any bigger than necessary. And we want it to match the manager so that the right thing is happening. Keeping in mind that we may run something and then come back right away, change a bit of code, and then run it again. So how do we make that work? All right, so we're working on a neat little toolkit called Pancho. Pancho stands for Python on Network. We couldn't figure out a good acronym, so we're just calling it Pancho. And it allows users to create and deploy self-contained Python environments at user level. So if you have a little JSON description of all your dependencies, so things in conda, things in pip, you pull things out of Git, you may have local files or HTTP files. Then we have a suite of 3 tools that using the things you would expect will analyze packages, create them for you, send them over, and run them. Now, I know what you're thinking. You're thinking, hey, what about containers? Okay, yes, all right. We do know about containers. People have been talking about this for a while. And I like containers. Containers are nice. Some of my best friends are containers. But it isn't necessarily the right solution to use in every situation. So for example, what if your worker is already running in a container? Because we had to deploy it somehow. Can we then get another container just to run the task? Well, most container technology is not particularly good about nesting. Okay. Well, all right. So we could use containers. Containers are nice, but you still have to solve the problem. What do you put in the container? That's kind of the harder problem that we're solving here. And furthermore, I'm not keen on using a tool that's too big for the job. So in this case, directories work very well for moving stuff around. And so we're satisfied to use. Right, so here's the idea. The idea is you have a stack of complex software here, and you run Pancho package analyze if you don't know what it means. And this performs a static analysis of your Python app and its dependencies and tells you of the things in your current environment, what do you depend on? Gives you a little JSON specification. And then you can take that JSON specification, which will pack up the dependencies you have here, whether they're standard or not, and then allow you to send them over to the other side in order to execute the task. Now, how you execute that environment, well, you got a couple options. You can either do it per task, you can do it per worker. In this picture here, what's happening is on the left, we have a specification, we make a package, and it gives you a tarball that represents the environment, and that's just a file. Because it's just a file, we can put it inline into a Parcel application so that it gets sent over as needed to workers that need that environment. And then when it is time to run a particular task, at that point, then we activate the environment through Python package run and then run the task. And so this is available in Parcel right now. If you flip the right switches in the work you executor, then you can send over the environment you need. It runs, bada bing, bada boom. Now, there's a downside to this, of course, which is it may not make sense to pay the cost of instantiating this environment for every single task. And although we do cache the data over there, and we also cache the deployment of the data, you still have to pay some cost every time you invoke a task. So you can turn it around. You can say, instead, what we're going to do is we're going to create the worker in the desired environment. So from this JSON specification, we'll create the package, make a tarball. And then instead of sending it over in every task in Parcel, what we do is we send it over when we create the workers. And so we do a Pancho package run to instantiate the worker in the environment. And then the worker goes and executes tasks as fast as it can with everybody inherent in the environment that it was placed in. This is probably the more performant approach. but it does require some changes to your deployment. So you have to figure out, how you're deploying your workers. Is it through HT Condor or Slurm or something else? And then make the necessary changes to your scripts and environments to change how things are invoked and passed around. All right, now I would say that
just a couple of minutes, okay?
So just first look at sort of orders of magnitude here. It is actually kind of interesting to understand the scope of dependencies and applications, and the results are honestly sometimes terrifying. So we have a couple different applications here: Shadow, TopEFT, and Colmena. I think I'll focus on Colmena since we already mentioned it here. The software dependencies for Colmena, when we do our static analysis, sum up to 4.8 gigabytes, which makes me a little nervous. Now, I'm not saying it's wrong, but it does suggest a very large footprint. In fact, even our smaller one here, Shadow, which it's 1.4 gigabytes. I think most of that is TensorFlow, getting the right version of TensorFlow packed up and sent over. So at the moment here, creating and analyzing these things is actually more expensive than you would think. And it turns out that most of the time is spent in solving for dependency conflicts. So as shown here, we have a column for no version specified and all versions specified. When you're working with Conda, if you know exactly the versions you need of everything, it goes through and finds all your packages right away. But if you have a whole bunch of conflicting requirements without specific version numbers, it can take a really, really, really long time to find all the necessary things. So I'm not quite ready to publish this yet. This is sort of a first look at orders of magnitude of what we're talking about here. I think there's some room for improvement and some newer things that we can do. So a couple questions to think about. Do we really need all this code just to send a function from here to there? I don't know yet. I think we have to figure out which of those dependencies are real and which of them are false. I think we need better tools for understanding the dependencies that we actually use in our programs and not just the ones that are declared. And we probably need to extend this dependency analysis to other kinds of resources. So I'll just throw that out there. And there's sort of one last thing I wanted to comment on. One thing we've been doing lately is we've been doing a whole lot of end-to-end integration tests of how things all fit together. So I can sleep a lot better at night knowing that we want an integration test to parcel a work queue on a real application. But sometimes terrifying things happen. So for example, CondaForge decided that Python 3.6 was no good anymore. And so the day before a workshop, which I'm about to talk about this integration, it decided to stop working. But fortunately, we're testing regularly for those things and keeping up with the community environment as it evolves. So if this sounds interesting, you can learn about WorkQ and friends in the parcel documentation. There's a quick start there for the installation. You can read our documentation. And also these bits and pieces can be used a la carte in different ways. So if Poncho or resource monitoring sounds interesting, those are executables that you can pull out and mix and match how you like. So I want to thank my students who have contributed to this work, the NSF for supporting us, and thanks very much.
Awesome. Thanks a lot, Doug. Maybe time for one quick question. Certainly this came up a couple of times yesterday, Doug, so hopefully this answered questions from people yesterday. So I see Matthew had a question about WorkQ resource integration for newer generation chips, such as AMD GPUs or FPGAs. You guys doing anything in that space?
Well, so we have very coarse support for GPUs in the sense that in the sense that if your application needs one or more GPUs, we can count them up and make sure that GPUs don't get assigned to multiple tasks simultaneously. That's sort of the level at which we're at. The GPU space is a little tricky because GPU resources are a big problem. There seem to be a multiplicity of ways for observing and managing those resources. And at the moment, at least NVIDIA is pushing this business of GPU virtualization, in which you divide up the GPUs in advance and then assign tasks to them. But I'm not quite sure that's the way to go. So short story, we don't have a lot in that space, but I think it's an important place to look next.